Good evening, everybody, and welcome to Astronomy Education. My name is Colin Hill, and tonight I'll be talking about the night sky. So I'll be going over some celestial terms, showing you how to navigate yourself around the sky. I'll be talking about the magnitude system, some star names, some deep sky catalogues, and then we'll wrap it up with a bit of a tour of some of the brighter stars that are up in the sky at this time of the year. But before I do that, I'd just like to acknowledge and pay our respects to the Gawler people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Gawler people to country, and we respect and value their past, present and ongoing connection to the land and cultural beliefs. So I'm just going to start off with going over a few celestial terms. The celestial sphere. So this is the sky considered to be the inside of a hollow sphere in order to describe the positions and motions of astronomical objects. About 2,000 years ago, the Greek astronomers actually thought there was literally a crystal sphere that all these stars are attached to, which obviously is not the case, but it is useful to consider it like that when we're trying to describe the motions of objects as they move around the Earth. Now, the celestial poles, so these are the 2 points on the celestial sphere about which the sky appears to rotate. So they're actually a projection of the poles of the Earth out into space. So if you say the North Pole of the Earth, if you project that into space where it intersects the celestial sphere, that's the North Celestial Pole. Likewise, the South Celestial Pole is a projection of the South Pole of the Earth out onto the celestial sphere. And the celestial equator, it's an extension of the Earth's equator out into space until it hits the celestial sphere. So there's the Earth's equator there. If you project that out until it hits the celestial sphere, then that's the celestial equator around there. And then the ecliptic, that's this yellow dotted line here. That's the path the sun traces out on the celestial sphere. Right, now we have a coordinate system for finding, or determining the position of objects on the celestial sphere. We have declination. Now this is equivalent to latitude on the Earth, and it's the angular distance measured in degrees north and south of the celestial equator. So northerly declinations are positive and southerly declinations are negative. So if an object was right on the, say, the South Celestial Pole, so that would be 90 degrees negative. And then anything on the equator would be 0. And then we move out to 90 degrees positive at the North Celestial Pole. Then right ascension, this is equivalent to longitude on the Earth, but it's actually measured in hours, minutes and seconds. Eastward from a 0 point, which is the intersection of the celestial equator and the ecliptic. So that's this point here, and it's known as the first point of Aries. So 1 hour of RA is equivalent to 15 degrees. Now the first point of Aries is no longer in Aries because of the precession of the Earth over thousands of years. It's actually located in Pisces, but it's still called the first point of Aries. More terms. The meridian, so this is the great circle on the celestial sphere passing through the poles and the zenith, which is directly overhead. Then the zenith is the point directly overhead. The zodiac, so this is the belt of the 12 constellations through which the sun's path in the sky, the ecliptic, passes. In reality, the sun actually passes through 13 constellations. The 13th is a Fucus. And we did have a president of the society many years ago who considered himself an Ophiuchian as his zodiac sign. Altitude, this is a local coordinate system relative to horizon, measured in degrees above the horizon. And azimuth is a local coordinate measured in degrees eastward of north. And I mentioned precession before. This is caused by the wobble of the Earth's axis over about a 26,000 year period. And it results in the celestial poles changing over time. So it's the Earth sort of like a gyroscope is sort of doing this over 26,000 years. So the position of the poles sort of gyrates around in the sky over that time frame. Now, return to the south celestial pole, because that's the one that we can see from Australia. So this is the point in the sky about which the celestial sphere rotates. So if you ever take a long exposure photograph at night, say over a few hours, you'll get these star trails. And you can see that the stars appear to rotate around a point in the sky. And that point in the sky is, from our point of view, is the south celestial pole. And its angle above the horizon, so this angle here, is equivalent to latitude. So for Adelaide, it's 34 degrees and 56 minutes south. So that's what that angle above the horizon is. Now, stars and objects that do not set. So you can see a lot of these stars from our location in Australia or Adelaide. These stars, they do not set. They're always above the horizon. So they're called circumpolar. So for instance, the Southern Cross from our latitude never sets. It gets very close to the horizon, but it never actually sets. So the entire constellation of the Southern Cross, or Crux, is circumpolar. The south celestial pole is where an equatorial mount's polar axis is pointed during alignment, which if you've ever done that, you would know that. Now we'll talk about the magnitude system. So this is a system of defining the brightness of astronomical objects. And it was introduced by the Greek astronomer Hipparchus in 129 BC. And he said that a magnitude 1 object is the brightest he could see, and a magnitude 6 was the faintest he could see. And it wasn't until 1856 that Norman Pogson formalised the scale and put it on a mathematical basis. So he defined a magnitude 1 object exactly 100 times brighter than a magnitude 6 object. So that would mean that a 1 magnitude step is a brightness difference of 2.512, which is the 5th root of 100. So you can see by that it's actually a logarithmic scale. Now, back in Hipparchus's day, he didn't consider objects brighter than magnitude 1, but there are objects brighter than magnitude 1. And if they are brighter than magnitude 0, then they have negative magnitudes. So, for instance, Venus has a magnitude of about -4. Now, we have two types of magnitudes. We have the apparent magnitude and we have the absolute magnitude. So the apparent magnitude is the brightness of the object as it appears from Earth. Right? So we look up at the night sky and the brightness of the stars that we see, those relative brightnesses, that's the apparent magnitude. But it doesn't actually show you what the absolute brightness of the object is. You know, very powerful stars could look quite faint because they're a long way away. So the absolute magnitude is the brightness of the object if it was 10 parsecs away from the Earth, which is about 33 light years. So if you could bring all of the stars to that distance of 10 parsecs and then compare their brightnesses, that would be the absolute magnitude, and that will give you an idea of the relative brightnesses of the objects. And that little diagram there, that sort of shows you what the definition of a parsec is. If you could imagine a star at 1 parsec away, there isn't any stars there, but imagine if there was, and if the Earth in its orbit created a right-angled triangle here with the star, using that 1 astronomical unit is like a baseline. So we have a right angle there. then that angle there would be 1 arcsecond. Right, and then that's the definition of a parsec, is when that distance creates an angle of 1 arcsecond. There is the distance of 1 parsec. Right, this table sort of gives you a bit of idea of the relative brightnesses of some common objects. Now, I'll put Vega there in red as sort of a zero reference. It just happens to be at about an apparent magnitude of 0, and its absolute magnitude is almost 0 as well, because if you put Vega at 1 parsec, it would be 0.5. And this is a factor here relative to 0, so obviously 0 relative to 0 is 0. Then as we go brighter, we got Sirius, the brightest star in the sky. It's about -1, and you see it's 2.5 times brighter than Vega because it's a logarithmic scale. And if you put Sirius at 10 parsecs away, it would be a magnitude 2. So a lot fainter because it's only about I think 6 light years away. Jupiter -2, Venus I said was -4, but it's 40 times brighter than Vega. Then we got the full moon, which is -12. So that's 63,000 times brighter than a magnitude 0 object. And then the sun -26, so it's 25 billion times brighter than Vega because of the logarithmic scale. Then if we go the other way, the star A Crux, the brightest star in the Southern Cross, is a first magnitude star. Gay Crux, which is the third brightest star in the Southern Cross, is magnitude 2. And then Epsilon Crucis, that's the 5th star in Crux. It's a 3rd magnitude. And you can see it's 15 times fainter than Vega. Then Omega Centauri is a globular cluster in Centaurus, visible to the naked eye. So it's a apparent magnitude of 4. Then Sigma Octans, so that's the south polar star, or the pole star of the South Pole. It's magnitude 5, so it's barely visible to the naked eye. And then Eta Carina, magnitude 6, is right on the limit of naked eye visibility. And you'd have to have a really dark sky to be able to see that. Then Neptune, we're looking at objects that are actually beyond what the naked eye can see at night. So it's magnitude 7. The Sombrero Galaxy, 8. Now Proxima Centauri, it's actually the closest star to the sun, but its apparent magnitude is 13. It's an extremely faint star, and even though it's the closest star to Earth, even binoculars can't pick it up. And if you put it at 10 parsecs, it would drop down to 17.5. Then if we go out to the limits of what Hubble can see at the edge of the universe, we're looking at about magnitude 27 or so. So that's 63 billion times fainter than the star Vega. So this sort of gives you a little bit of an overview of the magnitude system. Okay, now we'll move on to star names. Now, many of the brighter stars have proper names. Those names are usually have Arabic or Greek origins. So here's some of the names of some of the brighter stars. I've already mentioned Sirius, the brightest star in the sky. It's Greek. It's a Greek name and it means scorching. It's also called a dog star because it belongs to the constellation Canis Major, the big dog. Canopus, which is named after the helmsman of the Greek king Menelaus. So Canopus is a white giant star 200 light years away. So it's a long way away, but it's still the second brightest star in the sky. So you can see by that it is actually quite a powerful star. Rigel Centaurus, it means a hoof of the centaur. That's an Arabic word. Rigel means foot in Arabic. But it's better known as Alpha Centauri, and it's a triple star system, 4.3 light years distant. And Arcturus, that's the brightest star in Bootes, the herdsman, and this is a red giant. So if you have a look at Arcturus at night, you can actually see it is noticeably orange because it is a red giant, and so it sort of appears orange to the naked eye. Now, stars can also be identified by their Bayer designations. So Johann Bayer, he introduced the system in 1603, and it consists of two parts, a Greek letter and the constellation that the star belongs to. So normally Alpha, the first Greek letter, is used for the brightest star in the constellation, followed by Beta, then Gamma, and so on. But this is not always the case, but usually. As an example, Alpha Centauri, which already mentioned, is the brightest star in Centaurus, the Centaur. And then Beta Centauri, also known as Hadar or Agena, is the second brightest star in Centaurus. There are also many other star catalogues in use, such as the Henry Draper, the Smithsonian Astrophysical Observatory Catalogue, or SAO, Hipparchus, and many more. Now, constellations. Constellations are a formation of stars perceived as a figure or design. So there are 88 constellations, and they're named after characters from classical mythology and various common animals and objects. For example, Andromeda or Crux here, the Southern Cross. Now, many of the original 48 constellations were listed by Ptolemy in the 2nd century AD, and they originated in Mesopotamia and Greece. Because they were in the Northern Hemisphere, they couldn't see a lot of the southern sky, so that's why there were only 48 known back then. So the remainder of the 88 constellations, or the remaining 40, they were added since the 1600s. So this is when the European explorers started to sail south, and they catalogued a lot of the southern skies, and they named a lot of the southern constellations after a lot of nautical objects, like the sextants for the sextant, things like that, or animals. And the official boundaries of the constellations were defined in 1930. And constellations are useful for specifying the positions of celestial objects. Then we have some deep sky catalogues as well. So one of the most popular ones is the Messier catalogue. So this is 110 objects. These were catalogued by Charles Messier in 1774. He actually had no real interest in these objects. He was actually a comet hunter, and he was often confusing these faint fuzzies in the sky for comets. So he made the catalogue of these objects so that if he spotted them, he knew that it wasn't a comet. So, for example, M42 is the Orion Nebula. Yeah. Then we have the new General Catalogue, or NGC. And now this is 7,840 objects compiled by John Dreyer in 1888. For example, NGC 2070 is the Tarantula Nebula, down here. Then we have the Index Catalogue, or IC. Now, this is a supplement to the NGC in two parts, and it consists of another 5,386 objects. For example, IC 434 is the emission nebula surrounding the Horsehead. Now, that's this bright red region around the Horsehead. Then the Caldwell Catalogue. Now, this was 109 objects listed by Sir Patrick Moore in 1995. So these are objects that he catalogued that are viewable in a small telescope in addition to the Messier objects. So especially for objects in the southern hemisphere that Charles Messier couldn't see. For example, C103 is the Tarantula Nebula, which Charles Messier wouldn't have been able to see. Then we have some other deep sky catalogues. We have the Able catalogue. So this is a catalogue of 4,073 rich galaxy clusters, originated by George Able in 1958. So this is the Fornax cluster, or Able S373. The GUM catalogue. This is 84 emission nebula compiled by the Australian astronomer Colin at Mount Stromlo in 1955. Example GUM 39, or the head of the running chicken. The Barnard catalogue. So this was a list of dark nebula. So dark nebula are nebula like the Horsehead. We generally only see a dark nebula when it's illuminated from behind, like by an emission nebula or some bright dust or gas at the back. For example, B33 is the Horsehead Nebula itself. Then we have the ARP catalogue, which is an atlas of 338 peculiar galaxies by Hult and ARP in 1966. So ARP 244 is the antenna galaxies, which are two galaxies which are interacting or colliding. So they're sort of out of the ordinary. They're not sort of your standard galaxy. So he catalogued the peculiar galaxies that are usually interacting or they're all distorted. There are obviously a lot more catalogues than this, but that just gives you a sample. So as I said, I'm going to conclude with a little tour of the sky as it appears tonight. It's called the Heavenly G because these bright stars sort of form a giant capital G in the sky. So we'll start off with Sirius. So that's the star we've been talking about. It's one of the closest stars to the sun, and it's the brightest star in the sky. So the reason it is the brightest star in the sky is because it's very close, and it's also quite a bright star. It's about 26 times the luminosity of the sun. It's a white main sequence star. Magnitude 1.5, and it's also a binary star, so it's actually a two-star system. The secondary star is a white dwarf. So if you point your telescope at Sirius, you can often see a tiny little dot right next to the bright star, and that's the companion, the white dwarf companion. All right, and then we move around to Rigel. Now, I mentioned before Rigel Centaurus, which is Alpha Centauri. Rigel means foot in Arabic. So the star Rigel also means foot, but it's the foot of Orion. But because we're in the southern hemisphere, the constellation of Orion is upside down from our point of view. So even though Rigel's a foot, it's actually at the top of the constellation. Now it's Beta Orionis. Now, I said there were some exceptions. Generally, Rigel is usually the brightest star in Orion, even though it's Beta, but not always, because the alpha star is Betelgeuse, but it's a variable star, and you can see here that it varies between 0 and 1.3, where Rigel is a steady 0.1. So you can see at times Betelgeuse is actually the brightest star, but most of the time it's not. So whoever gave it these Bayer designations must have done so when Betelgeuse was at its brightest. So it's a blue-white supergiant star. It's about 90,000 times the luminosity of the sun. It's also a binary star, and it's over 1,000 light years away. And considering it at that distance, it's still a magnitude 0 star. It shows you it is quite a powerful star. I've actually imaged Rigel myself, and it is a binary star. And you can see the secondary star in an image, and it's just like a little pinprick of light next to a searchlight. And I did a bit of research and found out that the secondary star is 100 times more luminous than the sun. And yet it looks like it's just a little pinprick next to the searchlight. Moving around, we come to Aldebaran, which means the follower. So this is Alpha Tauri. So this is the brightest star in the constellation of Taurus. And it's a noticeably orange star, a bit like Arcturus. It's a red giant. It's probably similar mass to the sun, but it's exhausted its hydrogen fuel and it's turned into a red giant. As with most red giants, it's variable. So it varies between 0.75 and 0.95 magnitude, and it's about 68 light years away. Then when we head towards the horizon, we come to Capella. Capella is a yellow star. It's a similar spectral class to the Sun. It's a G-class star, but as opposed to the Sun, it's a yellow giant, not a yellow main sequence star. So it's quite luminous. So at 45 light years away, it's about a magnitude 0 star. Capella itself, it means the she-goat, because Alpha Auriga is the she-goat, and is also a binary star. So you can see most of these stars are binary stars. Most stars in the sky are multiple stars. The Sun is a single star, and it's in the minority in that regard. Speaking of multiple stars, we'll move to Castor, which is the brightest star in Gemini. Magnitude 1.6, and I've wrote here it's multiple star system. It's not a binary; it's a multiple star system. So when you look at Castor in a telescope, it looks like a binary star. You can see two very luminous stars, which are in orbit around each other. But each of those two stars is also a binary. But they're orbiting so close together, they're called a spectroscopic binary, because a telescope can't split them because the orbits are so close together. And in addition, there's another star orbiting those two, the inner two, bright pair. There's another star in a wide orbit orbiting the two bright stars. And it too is a binary. It's a binary red dwarf. So it's a 6-star system. Also in Gemini, we have Beta Geminorum, or Pollux. It's noticeably yellow. It's another evolved star that's moved off the main sequence, 36 light years away. And then we come to Procyon, which is the brightest star in the in Canis Minoris, which is the little dog. So Procyon actually means before the dog. And it too it's only 11 light years away, so it's a reasonably close star. And it too is a binary. And like Sirius in the big dog, its binary, its secondary star is also a white dwarf as well. And but apparently it's a very old white dwarf, so it's more of a yellow dwarf. And then we come into the centre here, and we end up at Betelgeuse, which we mentioned earlier. It's actually the hand of Orion. So it's sort of between. We have the belt stars and the Orion Nebula between Betelgeuse and Rigel. As I said, because we're upside down, this is his belt, and this is his sword hanging down from his belt. So Betelgeuse is a red supergiant star, and as I said before, it's variable. It varies between magnitude 0 and 1.3, and it's 425 light years away. So it is at quite a large distance, which means that it's a very luminous star. And if you could put Betelgeuse, replace our sun with Betelgeuse, we'd be inside the star. It's so large. In fact, the outer layers of the star would probably go all the way out to Jupiter. But because it's only got a mass of about 20 solar masses, to fill that volume, it's more of a hot vacuum than anything else. And that sort of concludes the talk. Do I have any questions? Peter.
So Castor, you said Castor was a agglomeration of 6.
Yes.
What's the average distance?
Between the stars?
Yeah, in a period, do they know?
Not really sure. I think between the two bright stars, they're in a fairly wide orbit because they're easily separated with a telescope at
because you got the 3-body
at 47 light years away. They're probably about several hundred astronomical units apart.
How many? 700.
A few hundred.
A few hundred
astronomical units apart, but because they are each of those stars is a binary as well. They would be very close orbits, probably only a few astronomical units between them that we can't separate from our distance here. Right. I'm not too sure about the red dwarfs. They're in a very wide orbit around the main 2 stars.
Okay, cool. Thanks.
Hi, yes, I have a couple of questions, if that's okay. So the first is about the catalogues. There were a number of double ups that you include. Is there like a standardized
double up? Did you say?
Oh well, yeah. I mean, like there were some objects that were in.
There's a lot of overlap between these catalogues. You know, like all of the Messier objects all have an NGC designation as well. Okay. So yeah.
So the NGC is the standard.
Yeah, it sort of encompasses practically everything, and all the other catalogues are like sub-catalogues of that. I'd say, like the Caldwell ones, all of those objects would have an NGC designation as well.
Okay, and then the second question is to do with the absolute and apparent magnitude. On the table you had, it didn't have all of the absolute magnitudes. Does that system still work for the early galaxies, which are very far away?
Like, for instance, the moon, it'd be meaningless putting the moon at 10 parsecs away. So that's why I didn't include like the planets and that. They'd be just so faint, it's just meaningless putting them at that distance.
Yeah. But what about like the faintest one that you had on that table was the early galaxies? What would that look like?
Oh, yeah, but you wouldn't want to put a galaxy 10 parsecs away. We'd be inside it.
Okay.
So once again, it's meaningless.
Yeah. Okay. So it doesn't really work. It's mainly for stars.
It's usually used for stars.
Okay.
Yeah.
Yeah. That's cool. Thank you.
Good evening. Deb and I have been going to some other lectures, and people have been using what the lecturer has been saying is old names, and there's new names for lots of stars now. Are any of these stars that you're talking about being renamed, and what's the reason for changing the names?
I'm not aware of any stars that have got new names. Have you got an example?
No, I can't. I'm 81. Memory's not the best.
Does anyone else know of any star that's been renamed? Yes, Werner.
Yeah. Some of them were Aboriginal.
Right. Yeah,
and some of them were other nationalities.
These are probably local cultures who've got
their fingers in them.
Got alternate names for stars, where these are probably more the astronomical unions, preferred names, I guess. Where a lot of cultures, would probably have alternate names for stars, like the Aboriginals, for instance. Yeah.
Okay.
Sorry? Are they?
Yeah.
Okay.
It's a bit confusing for a beginner.
It is, isn't it? Yeah, it's
you.
like a lot of the, like Adelaide's got an Aboriginal name as well. It's be something like that, isn't it?
Thank you. That was very informative. Two small questions. What percentage of stars are binaries or multiples overall? And do we understand the mechanism that produces a binary star system rather than a single star?
Okay. I think it's around about 70%, something like that, multiple systems. So it's most stars are in multiple systems. It's just like stars are born out of collapsing gas clouds, and they start to rotate, and they must be as they're rotating, they must get like two centers of gravity, which then pull in the gas, and because they're rotating, they're orbiting each other, and then they just condense into two stars. I believe that's sort of the mechanism. I don't know when it starts getting into multiple star systems. It must get very complex how they form. Sure, I can't give you a better answer than that. I don't think they're really sure exactly the mechanism, but that's essentially how they would be forming, I would think. Was there any online questions?
Yeah,
Werner?
check
Yeah?
that.
Or you're scratching your neck? Oh.
Not a question as such, just an interesting observation. The separation between Sirius A and Sirius B is pretty well the same as Rigel A and Rigel B, which is often nicknamed Nigel. However, Rigel B is a lot easier seen than Sirius B because the primary star Sirius A is so much brighter than Rigel A. It's just an observation.
The relative brightness is different.
Yeah.
Even though Rigel's still a lot brighter than Nigel, it's still a smaller differential than Sirius and Sirius B. Yeah.
And I'm not 100% whether, I reckon 95+% I've seen Sirius B. My telescope's got 6 diffraction spikes, so there's plenty of spots for Sirius B to hide behind.
I've imaged it. It's not that easy.
The other thing, it's Vega, not Vega. That's an American pronunciation.
I apologise.
It really grates me, that pronunciation.
God damn. A lot of these stars, you've got to be careful on the pronunciations. Is it Aldebaran or Aldebaran? Yes.
Sorry, I wandered in late, but probably another observation. 70% of stars are binary. I imagine that's reasonably fatal to life evolving on any of the planets that are involved in those star systems. I can't remember the name of that equation, but it possibly needs to be paid.
The Drake equation, was it?
Yeah.
They said they reckon it's possible if they're in a very wide orbit. Like Alpha Centauri, the separation between those two is about between like the Sun and Neptune. So it is possible for if planets to form, within about an astronomical unit, and they won't be perturbed too much by the other star. But if the two stars are in a close orbit, there's just no way that if there's any planets formed would be ejected from the system, probably. Yeah. Any online questions?
Sam Z is asking, are there any good textbooks that are for getting familiar with what was talked about tonight?
I have no idea. Visit. Sorry?
Yeah,
Colin's Stars and Planets. Visit the ASSA library, and I'm sure you'll find a book that will explain it all.
Absolutely.
Okay.
Any other questions at all?
All right. Well, thank you very much.